So I hope I have been in the last couple of discussion, I have been able to motivate all of you the nuances of a measurement, what are the systems that are required, and how do we view the operator in terms of the experimental physics. Okay. So what are the challenges posed by it in terms of interpretation? And moreover, since all the measurements are probabilistic in nature, how do we actually make it happen? So that was the first focus of our discussion in the previous two classes. And essence of or the importance of applying the knowledge of quantum, the postulates of quantum mechanics, which governs the entire creation of the physical system as well as measurement, action of an operator, how things evolve. So that is what we are trying to work around it. So entire quantum computation is nothing but implementation of those quantum mechanical postulates. That is a governing principle. Okay, so that is, if you understand that nicely, then I think you are all ready to become as a quantum computer technicians or operators or computer quantum computing scientists. Okay, so because there's not much into it except the challenge is, yes, easier said than done. That then why not so many people understand quantum mechanics? So why they have not been able to translate their knowledge into quantum computation? It is because the lack of technology available, and of course there is an improvement in the understanding of the subject also over a period of time. Because entanglement as a resource has been only used only in the last couple of decades. Though quantum mechanics is almost like this knowledge was there almost like 40-50 years back, but it took some time. So nevertheless, okay, so if you have any questions on the previous two discussion, you can please proceed to ask. Otherwise, I will start with the presentation. Anyone wants to ask about? Okay, okay then. So as I said, I am trying to use the textbook as my resource for displaying what I am going to talk about, and I've also mentioned the name of the textbook. So I'm just going to reproduce the section of the, I mean, I have a PDF file which I'm going to scroll down and I'm going to discuss based on that. Okay. Just starting the presentation. Just give me a couple of minutes. So is the screen visible to? Okay. So as we see that there are, we started the discussion single qubit system and then we moved on to 2 qubit system. And then eventually once we understand and create operators based on that, then it is a scalable physics, so it should not be a problem to introduce some additional complexity later on based on the algorithm that you would like to execute. But before that, we would like, so what the strategy as defined earlier was to understand the nature of this quantum based operators and gates, that is quantum gates as we call it as, and then show the parallelism between these gates and the classical gates for the simple reason that Classical gates, we have a very advanced competition in system in classical competition is in place, which carries out all the work for us, supercomputers and all. Of course, algorithms keeps changing and improvising to exploit the hardware which is available to us. So it makes sense for us that we should try to show the equivalence of the quantum gates with its classical quantum classical counterparts. And if you are able to show that, then we are in a position to not only reproduce the results of what is based on classical computation based calculations, but also much more than that. So it will be slightly a kind of a what is called as a more information can be obtained by using. I mean, of course, not information. I would say. I mean, the advantages of quantum mechanical systems may be exploited further. So that is what we'll be doing, and then we'll list down the proper criteria which we have been discussing. So more or less, we have already laid down the foundation to come with the physical criteria, but we'll formally lay it down under D, what is called as the D Vincenzo criteria. So towards that end, so we are considering a two-qubit system. So the two-qubit system, as you know, that the basis vector for that. So any quantum mechanics or any like physical system, whenever we try to do, we always come with a classical what is called as frame of reference, because physics is always taught in some certain frame of reference. That is very important for us in the laboratory to understand the result and all. So the partly the reason why we try to choose an appropriate frame of reference or what is called the basis vectors in quantum mechanics is that these are mostly we are dealing with an orthogonal system. We are not considering any non-orthogonal system. And of course, the definition for basis vector is that they should be mutually orthogonal, and the measurements are always done on those basis vectors. So it's always a projection on any one of these basis vectors, and the overall vector is known by measurement of the projection along each of those basis vectors. Right, just like a position vector in Cartesian coordinate system, you write as ax cap, where x cap is your unit vector along x direction, by cap, where y is unit vector along y, and plus z cap. So a, b, c determines the length of the vector along each of them, and in some linear combination, it will represent a position vector, which will completely map the entire space for you. Right. So you can see that the power of resolving anything in the basis vector is extremely. I mean, the need for resolving the basis vector is that you can express any other vector in terms of a linear combination of it. Okay. So that is where we as physicists always strive to identify frame of reference, define certain things along that quantity, so that we can carry out the measurement along along the projection along those basis vectors. Okay. So that is one thing which you have to remind yourself whenever experiment you are doing. Whether it's an electronic experiment, electrical experiment, magnetic experiment, optics experiment, you name any kind of an experiment, there has to be a basis vector which defines the system. In classical case, we say it's a frame of reference. Okay. So I hope everyone is with me, everyone is able to listen. Okay. Okay. So we have this two qubit system where we define now instead of 0 and 1, it is referred as in terms of direct product, which is 0, 0, 0, 1, 1, 0, 1, 1, where 0, 0 is defined as 1, 0, 0. Of course, this is transpose, so normally we write in terms of column vectors. The other qubit will be 0, 1, which is nothing but 0, 1, 0, 0. Then the third qubit is 1, 0, which is a column vector of 0, 0, 1, 0. And the fourth qubit is 1, 1, which is described as 0, 0, 1, 1. So this definition for a two-qubit system forms the entire basis vector. Okay, so this is one thing which one has to always bear it in mind as we are trying to do. So last time we saw what is called as a function of the C naught gate. Not gate is nothing but negating the bit, which is the incident bit. So it flips the gate. So that is done by the Pauli operator X. And then we have some phase addition of Y and Z. So a combination of that will give you a different kind of a bit. So Pauli operators as well as the NOT gate and the identity operator form the single qubit gate. Now if we add one more qubit, we can improve the functionality, and this is called as C naught, is nothing but controlled NOT, what is called as. That means not all the gates will be flipped at the same time. Only under certain conditions it will be able to do it. Okay. So that is what we have defined, and this function is given in the matrix form as 1 0 0 0 1 0 0 0 0 1 0 0 0 1, and then the C naught gate is 0 0 1 0. So you can see the change which has occurred in the normal basis vector in this last, the fourth quadrant of this matrix, I would say. The third quadrant, if we define as 1, 2, 3, 4. It depends upon how you define the quadrant. So let's say I started 1, 2, 3, 4, going in the clockwise direction. So normally, if I have to define this gate, it will be 1, 0, 0, 1, 0, 0, 0, 0, 1. And that action is being defined by this multiplication of these two vectors 0, 0. Now you remember that this 0, 0 is not complete 0, but it is 1, 0, 0, 0. And then you are spanning this entire basis space over which this measurements have to be done. Now, one thing which I just want to impress in passing, which of course all of you know, we know the action of the C naught gate operator, which is given stated in this form. That is 0 0 is taken to 0 0, so it preserves as it is. Okay, and same thing is 0 1 is also preserved as 0 1. Okay, but whenever it is 1 0, then this is a control qubit 1 and target bit is 0 here. So this gets flipped when the control bit is 1 there, and that is what 0 becomes 1, and that is where it is written. And same thing happens here. So since control bit is 1, it flips the other bit as from 1 to 0. But in the basis vector, if you choose, if you look at it, it seems that these two have flipped among the positions here, whereas these two are retaining. So hence, when you are having the flip of the state, we say that it is a negation vector, and that is only in the presence of the first qubit as 1. Okay, so therefore, hence it is called as control qubit. And the action of the operator is that it will act on the entire space of the given system, and hence, so these are the possible results. So we require to construct that entire space, and if you have to write down this operator form of this control NOT gate operator operation. So what we always do is we take this outer product of these two vectors or the basis vectors, the input and the output, so that all possible combination which is possible under the operation of this C naught gate will be emerged, or on which, so this the action of the C naught gate is that it will act on all possible. It does not know where the operator means I'm trying to find something. Let's say it's a measurement operator. I want to locate where in which state the lower state is. So unless and until I look it everywhere, okay, the idea is that I would like to search where that operator will be, where in what state that system is. I don't know. So what I do, I look at every possible way, and that action is done by taking the outer product of all the possible combinations of your uh, gates, which is the input and the output possibilities. Okay, so if you find that somewhere among this linear superposition of these outer products, the vector will be found, and this will act. So therefore, when I'm writing it in the operator form, that is bracket vector notation, or when they're writing the matrix form, this will act on a given basis vector. Okay, and then it will project it onto the some number with some probability, depending upon which state it is. That probability will be the what is your eigenvalue. That is where it has projected into the given state. So that is what is being done. So I just revisited this thing what we discussed. I thought that it may be trivial for you, but I thought it's worth mentioning when you talk in terms of common language. What is the action of this outer product? Okay, because it took some time for me to appreciate this. Only when I started doing experiments, then I realized the power of this outer product. Why people see there are two kinds of product vectors, right? One is the inner product and one is the second is the outer product. The inner product, which is called the projection operator, which is the thing which is used in the measurement of any vector. And if you want to act a given system, that you want to take a superposition, like you take a combination of all possible vectors and you want to act on it simultaneously, then that action is done by this outer product. So you have to fan out in all possible space. So which can be written in the compact notation. So you can separate this as 0, 0, and this will be multiplied by the identity vector. And this one state is going to be flipped around, and that is why it is multiplied with the negation vector. So if you think about this action of this C0 gate and the basis vector on which it is acting, then it is possible to just intuitively write down this kind of an operator form of the given C0 gate in this particular case, or any other unitary operator which is going to be used to carry out the computation. Okay, so far so good. And then since we demand that this has to be, this is a U stands for unitary, so you always take you check whether U dagger is equal to U inverse. Okay, so or U dagger into U should be equal to an identity product. So that is the basic criteria which one should be always verify whenever you're constructing any given operator. So that is a recipe which is going to be used for constructing any other form and an operator which is can be accepted as a quantum computational operator. Okay. So there is another interpretation for this C0 action is that it is an classically it is an action is just like an addition modulus 2. So which is in the Boolean algebra it is written as B exclusive or 0 is B 0, 0 1 gives 1, 1 plus 0 is 1 and 1 plus 1 is 0. Okay, so that is what is written. So classically, it is shown as a classical action of a C0 gate on the input state ij is written as I into I plus j, where I plus j is an addition modulus 2. Okay, so j is any other state in the basis vectors here. Okay, so this state is transformed into this one. So what are the challenges posed for us in this when we are writing the gate? We have seen that we require the essential criteria that it has to be unitary. It has to be an eigenvalue operator because we are going to do some measurements on this system. Now, this is one more thing which we would require to do. If you can think over it, I will give the answer towards when I try to conclude my discussion in a couple of presentations. So now there are two kinds of an operator which we are going to discuss in the quantum mechanical language. Okay. To know which state it is, whether systems are in real or non-real, You require what is called as a Hermitian operators or real eigenvalue operators. Okay. So to know which state it is, you require those operators, and you require the system is a physical. That means it's very much real. So those are only those class of operators will give you the physically verifiable results, which I can do or execute in the measurement in my laboratory. Okay. So does the action of any of the operator where you don't do a measurement. Now there are two things. Okay. One is you act on certain system and leave it there without knowing where the system is. Okay. That is, I shine the light on a system and I don't want to measure it. I don't know what I've done. I don't know whether it is light is being absorbed by the medium or it is re-emitting more light from the medium. Okay. So that is so there are two ways I can interpret. One is that the presence of light is going to alter the situation of a given state. So we say that the gate operation like not has performed will perform there, and only when I look at the output that the presence or absence of the photons will tell me whether the system has absorbed light or emitted light, thereby revealing in which state it was. So before we shown the light, we don't know. So that is an ignorance. So therefore, we write it in terms of the superposition of both the ground and the excited state in a given two-level system with certain probability. Okay, so if you don't know, then maybe probability can attach half of it maybe here in ground and then half in the excited. But the presence of the operator is going to alter that situation. Okay. Now, if I create a system, you have more number of two level systems without measurement. I choose a unitary operator which belongs to that particular class of the physical system considered. Does it really require it to be Hermitian? When you're performing in your operation, so of all the story, I'll just summarize and ask you a very simple. Try to ask you in the simple language. Whatever the action of the gates, what we are discussing now, does it always yield to a measurement,
No, sir.
or it only creates a class of a different state of a given system on which it has acted? Okay. So, if as someone said that it does not, so does it restrict or does it give you a more option of finding different set of operators which will act on the given system such that a different set of linear combination of those basis vectors are created as a result of the action of the given operator of the resultant gate operation, let's say. Because measurement is definitely a projection measurement. So whenever I'm going to do that, so if I take an inner product, let's say if I want to know which state it is, what is the action of this, then what I do, I take this and take an inner product with this, right? So I have to, if this is the thing, then I will multiply with this one vector. So it will give a projection into one of the basis vector where it is to be found. So that is the action of the measurement operator, right? It will always yield into some projection based measurement. So that will be the difference on the gate operation and the measurement operation. Okay. So there is one state where you create a superposition of the state because it is slightly difficult. I mean, it's I don't know whether I'm able to convey my enthusiasm and appreciation of this fact that because we are so much classically wired of thinking that if I, in terms of Boolean or digital electronics, if I have states of 1 and 2, I'll always have some measurement at the output end. Whereas quantum mechanically, I say that no, I don't know the measurement because yeah, just 1 second, I'll take this call. Yeah, sorry for that. So whenever I have to do a measurement, I will take an inner product or the projection operator, and whenever I have to span the space, I will take an outer product. Okay, so that is why all the operators are written in terms of the outer product, which gives this matrix form. Okay, so yeah, so that is a thing which I wanted to convey since this was discussed. So, yeah. Okay, so as we discussed, this is a what is called a graphical representation of the quantum circuit which is going to be used. So you have an this is the flow of data is from left to right denoted by a straight line, and any operation will be an interrupted in this flow of line. So that will be an unitary operator, and whatever result comes as an output on the other side. And if you have so for every data you'll have that many number of parallel lines. So if you consider a 2 qubit system, then under this control bit and a target bit, so whatever the bit I suggest, so what you know the action of this C naught gate. This is an action of a C naught gate where only when the control bit is 1, this bit will become 0. So I can write my bits state of the bit which is here 1 0 0 1 what 1 or 1 0, and then corresponding you write the output in this side. So that is how this action is denoted. And there is something called as controlled instead of this this is for the conditional negation, so this is for a C naught gate. Similarly, I can have a what is called as controlled unitary operation, that is control U gate, which is given nothing but instead of the negative you have written as X, which flips the state. You act on any given operator U, unitary operator U, acting on this particular state or the outer product of 1 1. Okay, and therefore it is written graphically as control and target. So that is just a definition to be introduced, and then you can find out the output for this upside down C naught gate. This is a basis vector given. So you take 0 0. So this is 0, this is 0 at the one stage, and then you see what the action flows here. Now you can see it's an upside down. Only when this is going to be 1, this state is going to be flipped here. Okay, so based on that you can do this exercise and find out what is the result here. So I think these are circuits are self-explanatory, and as shown in this circuit, all the operation is going to follow sequentially from left to right. Okay, So first this operation, then the resultant of gate will be used as an input to the next set of operation, and then so on and so forth for the third operation, and then what you get is the output here. So for given input, you get the output on the other side. Very much like what you do in digital electronics using NAND and XOR gate and other gates. Okay, so there is one more important class of gate called a Stoffel gate or control node gate. Okay, so yeah, so there what we do is we have 3 qubits where 2 bits are called as control bits, and the action of is that only when bit 1 and 2 are 1, the target bit is going to be flipped. Okay, so I get a much more better control of it, and that was necessitated for some particular reason, which we, when we discuss about some algorithms, it will be clear what is the importance of this. Okay, why do you require, when you can do with one control bit, why do you require 2 control bits here? Because some experiments do require, like when we, in a short while, when we try to design what is called as an OR gate using the CC NOT gate, then you will understand what is the role of this control bit. 2 control bits. I mean, it is there. Yeah. Okay. So sometimes more than one qubit is required. Yeah. This concept. So having moved on, so that is what was discussed and we stopped there. So this is now an very important class of another gate, what is called as a Hadamard gate, which induces a transformation which creates, because all this the whole power of quantum computing is based on creation of the superposition states. So to start with, when we are trying to ideally start our quantum computation, what we do is we try to create an initial set of states. So that means, it is very, very important. You cannot have any random number of, distribution of any element in different amount of states which you are selecting for computational purpose. Because computational is a very, very uh, directed calculations, in the sense that I require to know which state it is. Like as I say, if I have to add 1 to 0, the output as 1. So in that case, 1 and 0 has to be precisely defined. If I take an unknown state, I don't know what I'm adding to 1 to, so I don't know what will be the result. So therefore, there is a need for defining the states properly first, whether it's in the ground state or excited state, but the knowledge should be there. And we say, what we say is, we'll have to prepare the state in unambiguous fashion such that all the states are in the same level, or all the bits are in the same state rather. Okay, so only then we can act any given operator. Now if that is so if all the states are in the 0 0 state, then what is the fun? Then all the whole discussion about acting any unitary transformation, unitary operator or gate operation on this is going to yield the same result. Because when you're trying to do the computation, you require to create a superposition of the states. Okay, in certain cases. So for do that, you require an operator, which last time I mentioned in passing about what is called as the NMR gate, pi pulse and other thing, pi by 2 and 2 pi pulse in the NMR quantum computing case when we are trying to discuss. That is the time duration of the pulse over which you can create a superposition of the states between the two. So that action is called as an Hadamard operation, where pi by 2 pulse in the NMR, which creates a superposition state of 0 and 1, is that action is done by the so-called Hadamard transformation or a Hadamard operator. So what does that do? It creates a linear superposition of the states 0 and 1 such that the 0 will be taken as 0 plus 1 divided by 1 by root 2, and 1 is taken to a state of 0 minus of 1. So there is an extra phase factor which is introduced in this linear superposition. Remember, this is exponential I pi. Okay, so I pi is nothing but minus 1 value. Okay, so it's a superposition of that factor which is 0 1 with the same weightage factor. So once we have this particular combination of this superposition of it, then what we have done that we have created linear superposition of the states on which any other operator can act, and we can perform computation on that particular basis with that. Because even though we have to start with any computation, we may work only with the zeroth state, but the entire computing power is fully used only when you have superposition of these two states 0 and 1. Okay, so that is the action. So that is what is done by this Hadamard transformation. So it is used to generate a superpositional state from 0 or 1. So if it is initial state in 0, it will lead to superposition of 0 and 1. If the initial state is in the 1, then it will lead to a superposition of 0 minus 1. So the signatures are very distinct. Okay. So the action of it is that it is going to span the whole space. So thereby I can write them in a matrix form as, so I take the outer product of these two operators 0 into this, because this is my initial target bit and this is my input bit. So that is where I am spanning this space here. Okay, this is 0. Here is my input bit and this is my output bit. So the product of the outer product of it is going to span the entire space, and similarly for the other combination. To add all this combination will result into my matrix form, which is 1 1 1 minus 1. So it is very different than your identity matrix or any other matrix which you have come across now. It's a very unique thing. And Hadamard gate is represented by letter H. Okay. So now, if I have n number of states, then I can generate, by action of this Hadamard transformation, I can generate all possible 2 raised to n states. So you can see immediately the power of this Hadamard transformation is that all possible supercomposition, linear superposition, linear combination of these states can be generated by just applying this operation on each of these qubit of the states here. Okay. So for each qubit, one Hadamard operator is going to act on it, and it will take in the superposition of these states. If it is initially in the 0 state, then you will have this particular combination 0 1 0 1, and I define this x as a combination of 0 plus 1. Okay. So that is, so therefore, and as so the question is now whether it is a quantum mechanical operator. All that you have to do is prove its unitary in nature. Okay, so you take this operator form of this one, and this is UH. So you take UH dagger, take the product of UH dagger U, and see whether it reduces to identity. Okay, so you take a complex conjugate and inverse of it. So you can write down that matrix form, multiply these two matrices, and see whether the resultant matrix is an identity. So that test you have to do, and that will be left as an exercise for all of you. So whatever is left as an exercise, expect that it will be part of your examination later. If there is some difficulty before the examination in not proving or whatever the exercise which is left to you, if you're not able to do it, you can just post that question to me. I will send you the answers. Okay. Now this is another way. So this is an exercise 4.4. Show that Wn is unitary in nature, which I just mentioned. So W is the one which defines your Hadamard operation. This is UH. Okay, so what is, yeah, so sorry, WN is something very specific. It is, I missed that point to discuss. So to produce, therefore we produce a superposition of all the states x with 0 less than or equal to x 2 raised to n minus 1 simultaneously. So this action of H on n qubit system is called Walsh transformation or Walsh-Hadamard transformation, and it is denoted as Wn. Note that when you are performing only one operation, one unitary operation, one time, that is H acting on a single qubit, so that is which we know is a Hadamard transformation. But when you act on n number of states, then it is called as Walsh-Hadamard transformation, where it is defined as Wn plus 1 is equal to unitary Hadamard acting the direct tensor product with Wn. That is a Walsh transformation. So that is the definition. And then, so the question here is show that Wn is unitary. So you have to take this in the operator form, UH. So this is in the operator form. Take the inverse of it and so, and yeah, you know what to do with the you to show it as unitary. You take the complex conjugate of this vector and take the multiply it with this way the original vector and show that it is results to unity identity matrix. That is, if you are able to do it, then that is you have answered this question. Now, so far we are writing this equation in terms of Hadamard transformation. So what is this surface below? I'm just describing what does the question means. So I'm giving an input here, let's say 0. So with that 0 state, I'm going to create a superposition of the states 0 plus 1 into 1 by root 2. So that is what is going to be in action. So instead of a single qubit, I'm now remember this is not a 2 qubit state, but it is a superposition of the two basis vector acting, which is the result of this Hadamard operation on the initial qubit here. Okay, so that is what is going to be. So it's a linear combination of a state is a state itself. It is one state. It is not a multiple state. So what I'm trying to say is when I have this action of this Hadamard, I don't view it as a separate two states here. It's a combination. So like 50% probability that it is in ground state, 50% probability it's in the excited state. So that particular combination is considered as a one state. If this factor of 1 by it was not 1 by root 2, let's say some other weighting factor, let's say I add 0.70 plus 0.31 one vector, so that will form another state of the vector. Okay, so that will be still a single state where the probability of finding the system in the zero state is 70%. The probability of finding this system in the state 1 or the excited state is 30%. So that is one state. Okay, so a linear superposition of state does not mean that it is it's a combination of many states. Okay, it's a quantum. So this is one more thing which you have to bear it in mind. Whenever you're creating a linear combination of any state, it results into only one. Quantum mechanically, it is treated as a one state. It is not an n number of states. Okay, so that is what you have to bear it in mind when you're trying to solve the problems as given in the circuit. So it leads to a superposition of 1 plus 0, same thing over here. And then this, based on this particular action, you have to perform the operator. Okay, so this is a control bit and this is a NOT gate. So this is an upside down control NOT gate. And then whatever the resultant you have to show here and show that the entire action of all this operator is nothing but a control NOT gate, that is a C NOT gate. Okay, so Okay. So these are other some questions which is given. So Q1 and Q2 is just a very general state. Hadamard acting on this, and then now you can see. So instead of one, so how are you going to treat the superposition of a linear combination of a gate, which is an input at the control gate, and what will the action on the target bit qubit here? And of course, it's a two qubit system, so the basis vector are 0, 0, 1, 0, 1, 1, 0, and 1. Okay, so this is the input which is being taken as for Q1 and Q2. So you can just post the solution. Whosoever is able to do it, you can post the solution. And if someone has access to this PDF, the answers are given at the end of the chapter book itself. You can verify it. If you have difficulty in understanding, of course, you can let me know. Okay, so far, anything you would like to proceed to ask, or should I proceed? Okay. Any questions? Yeah, please. Okay, you can still attempt to do something. Hmm. 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 Okay. One thing which I will tell you is I don't know whether I understood it completely, but I can appreciate your confusion that if the initial state is, I mean, I will try to rephrase your question. You tell me whether I'm close to what you're thinking. Okay, so the initial states are in 0, 1, and I apply a Hadamard transformation. Okay, so it gives me a superposition of state 0 and 1, ket 0 plus ket 1. And when the initial state is in 1, it gives me a superposition of ket 0 minus ket minus 1, ket 1. Okay, so that is what these two linear superpositions, superposed states, is a resultant of this Hadamard operation depending upon the initial condition. Now, what is the significance if I have to do it in physically? I mean, so I identify an operator which I call as an Hadamard operator and try to create the states, which is superposed states. So my difficulty is how do I introduce that sign of minus in this superposition state? Is that what I understood it? Is it close to what you're thinking? Okay. So can you elaborate it further again for me? Hmm. No, no, we are not representing. It leads to that state on a measurement. Okay. So see, when you are trying to do a measurement, you have to also create a separate operator for that. Okay. So what is called as measurement operator or the projection operator. Now here, if you look at, I can write the same second, the first qubit, I mean, get vector 1, which evolves as get 0 minus. So I can write that instead of minus, I can write as plus minus 1 raised to or e raised to I pi acting on the state 1. Okay, so what does it mean is that it has an additional phase of pi as compared to the this will be always be the numerically it will be equal half of either in this state or that state, right? Because if you when you're trying to do this probability or do the measurement, because if I take 1 by root 2, it is in equivalent. That's what I said when I'm trying to emphasize that 1 by root 2 into so when I'm trying to do a measurement on this state, so this state has a probability. So it will 1 by root 2 into 1 by it's an amplitude. So it will go square. Okay. If you take the direct of these two states acting on it, it will come out to be half of in front of it. Because e raised to I pi into if I take a complex conjugate of that, because that is what we do in the Hermitian operator, that e raised to I pi will cancel e raised to minus I pi and then you will end up having 0 or 1. E raised to 0, so that is 1. So the probability amplitude is half of for both of them. So what will be the difference? Okay. So I will lead you to this question to an interference experiment. I think all of you are familiar with the interference experiment, right? That you take two light beams which are coherent in nature, okay, and interference is nothing but superposition of the two states. So what you observe on the screen is the square of the superposition of the amplitude which is falling on the screen. What does that mean? I have from a single source of light, I split them up. I take a let's say double slit experiment or a Fresnel biprism experiment. So I've created two sources of light, and from these two sources, at a far off distance on the screen, the light is superimposed on the screen. So let's say slit 1 is 0 state, slit 2 is ket 1 state. Now what is the linear combination which is I'm seeing it on the screen? So I define 1 plus 0 as the bright light, 1 minus 0 minus 1 as the dark light. Okay, so if that is a superposition, what has that done? Why I have chosen this? Because when I write that 0 minus 1, I am writing as equivalent as 0 plus e raised to I pi into 1. So e raised to I pi is nothing but an additional phase difference which I have introduced in the second source. Okay, both the sources are to start with are coherent, so that means they have the same phase. And then I'm additionally introducing some path difference such that the phase difference is minus e raised to I pi, such that they destructively add on the screen and produce a dark position. So if I am looking at the projection of this superposition of these two states because the resultant of this Hadamard operation, I'm looking at the dark and the bright fringes because both are superposition, right? If I take the vector E1 is the vector of the light falling from the slit 1, E2 is the vector of the light, electric field vector of the light falling from the slit 2. On the screen, I am acting vectorally E1 plus E2. And then I write down the electric field expression for it, including the phase factor. So when I do that, depending on the position of the screen, that so I'm looking for a particular state of light. Now I'm not looking any random in between points, okay, because I have a factor of 1 by root 2 there. So I'm looking for the superposition of these two light vectors such that there's a phase difference of pi between them. Okay. So if I add those two vectors and try to see the resultant of it on the screen, it will correspond to lead to destructive interference. Whereas the other one will lead to constructive interference. So that is what so that is an additional feature which the quantum mechanics allows you, which classical physics does not. The role of the phases, which is exploited in this computation, which is generally not in the classical cases. In classical computation, we don't worry about the phase at all. Everything is amplitude based computation. The richness of quantum mechanics comes from its ability to use the wave function, which has a phase factor on it. So it's extremely sensitive in what kind of combination the two wave functions or two wave vectors add up or they are superimposed. Okay, so that's what I can. Does it answer to your question? Yeah. Mm-hmm. Yes. Yes. That's right. The fact that you have placed the screen on it, that is allowing you to collapse into some state, and that is the act of measurement. That you are trying to measure. See, eye is also a detector, right, for you. So, yeah. So eye is performing in combination with the screen. It's trying to find out which is dark and bright figures. So the moment you place the screen, which helps you to see the what is the state of the light at a given position, that is an act of measurement. Yeah. Any other question? Okay. I'll just take some water and then I'll proceed. Is it very trivial, the discussion which I'm involving in? Is it trivial for others? Do you know all these things already, or because we are revisiting quantum mechanics? That's all we are trying to do here. Uh-huh. You're considering it? You're considering what? Okay, so you're able to appreciate what you're doing now. Okay, okay. Good. It is useful to you.
So one question.
Yeah, please.
It's previously we saw that using the Hadamard gate we can generate two superposed state from 0 and 1.
Mm-hmm.
So sir, both have those equal probability, and like you said, we can just introduce, like in light experiments, we can introduce phase for
Yeah.
coherent states, and we can differentiate between them.
Yeah.
So sir, for like quantum superposed state like this, which have equal probability of 0 and 1, so
Mm-hmm.
like suppose we, for an example, I'm saying that we put a Hadamard gate and pass 0 state first and 1 state secondly. So sir, both will have the same probability of half and half for 0 and 1 after passing through the state. So how do we differentiate between the 0 and 1 initial states before they pass through the gate?
Yeah. So that is where the reversibility you have to work out, right? So in this example, what you have created is just a superposition of states. So what here the question which you are posing, how do I know which one is zero, which one is one? Right?
Yes,
Is it?
before passing the gate, because
Yeah.
after passing the gate, they both have the same probability. The only difference between the states are this minus and plus sign, but it does not come into the probability, right?
Well, the phases are defining. You have an eigenvalue which can go 1 to minus 1, right?
Yes, eigenvalue will be minus 1 and plus 1. Yes,
I mean, that is, see, that we can, okay. So I will put the question in this way. What I do a measurement on the same experiment. I'll continue with the discussion on the same experiment. That I'll measure now, as it was pointed out, that I put a detector and measure the intensity of the light. Now, this Hadamard transformation, when I'm trying to do, there is a intensity modulation which goes from I max to I minimum. In ideal case, I minimum will go to zero and I max will go to four times the I, or the intensity of each light source. Okay. So if I am having an equal probability of 1 1, then, or half of, then the intensity distribution which I'm measuring. So what is this Hadamard transformation saying? That I'm looking at a point which is called as I maximum, which will correspond to 0 plus 1 state. If it is I minimum, that location will give me the superposition of the states from 0 minus 1 state. Okay, so because that is the only two states which I am from the entire screen, I am only picking out only 2 points, which is I maximum and I minimum. But you know that the light is increasing and decreasing between I max and I minim periodically across the entire screen. So the intensity distribution says that they are acting uh, in an unequal contribution. Okay, so that I max and I minimum can vary. If I take some other value, then it will have a different value of probability. So more of one and less of other will be interacting there. Okay, so that is how I can interpret the intensity measurements of the interference pattern on the screen in terms of probabilities. Now, to precisely know which is 0 and 1, then I have to do something more to this gate. Okay, I require to transfer some more knowledge so that the process becomes new. Because once this measurement is done, that information is lost. All I can say that speculate what could be the initial state of the given system and how it has superposed to lead to the what you have seen. That is all I can say from this particular measurement. I cannot answer that question just looking at the measurement which one is 0 and which one is 1. For that, I require to transfer some additional information, which is a carry forward, okay, which will make this gate reversible. So, in fact, this leads to the next question, a very important one. how to make this unitary gate reversible. Not all the unitary operations are reversible in nature. Okay, and why it is required to make the unitary operations? Quantum. Why do we require states in quantum circuits to be reversible? Because classically, 0 and 1 are available on demand. You can always create initial states and then carry on the operation. But in quantum mechanical, once this leads to the collapse of states, okay, I create a superposition from the initial basis vector, but once the operation is done, then some of the operations are irreversible. I don't know what has happened before. Not all of them. That is why I'm making sure that it is all unitary. But if I further I require the knowledge of the state of the original system, then I require to create an additional mechanism. Okay, and which is the essence of the what is called the Toffoli gate. Okay, because I'm passing on that information, just carrying forward 0 0 control 1 control bit, and that is what I said that that forms a very important gate for two purpose. It can of course lead to creation of what is called an OR gate, and the other thing is that I can carry forward the knowledge of the state of the given system. So that is to say that I do a measurement on the partial thing on the initial state somehow and carry that information forward so that they are available for further gate operation. Okay, so that is what we will do. So from the given experiment, it's not possible to find out whether it is 0 and 1, which one is 0, which one is 1. Okay. You can just speculate because both are having probability half.
Sir,
Yeah,
can I say something about that? That
yeah, please.
thing how can you measure? Like theoretically, you can do like this. Like the output value are here 0 plus 1 and 0 minus 1.
Hmm.
So instead of measuring in basis 0 1, we can measure in a different basis. And the itself basis like 0 plus 1 and 0 minus 1, they also form a basis.
Yes.
So if we set up a different measurement technique to measure in that basis, then we
Hmm.
can differentiate. We can get the result. Here applying the, as I said, okay, 0 is there. Apply a Hadamard gate. We are getting 0 plus 1. So
Hmm.
in the gate we can apply another Hadamard gate again. Then we
Hmm.
can measure. Then we can find 0. And for the for input 1, the same case we can do. So the Hadamard gate produces a result 0 minus 1. So we can
Hmm.
apply another Hadamard gate. So we will get back the result 1. So
Hmm.
this Hadamard gate and then measurement, Hadamard gate and then measurement, these together can also form a measurement in a different basis. Like we can say in the 0 plus 1 and 0 minus 1 basis.
Hmm. Yeah, you can do that. I mean, it is like something like using the polarized states of light.
Yes,
Okay,
sir.
I take a linear and that is linear horizontal and vertical states, and I introduce a quarter wave plate and let the polarized light fall exactly at 45 degrees to its optic axis, fast axis. It creates, now you don't know whether it is at 45 degree or 135 degree to the fast axis, of plus 45 or minus 45 to the fast axis. So as a result, it creates a what is called as a right circularly polarized light and a left circularly polarized light. So that is also a combination of 0 plus 1 and 0 minus 1. Okay, so when I'm, but I don't know, I know that it is circular because when I take an analyzer and I try to do an intensity measurement, in both the cases, the probability will be continuously, it is at any angle you measure, the intensity will be the same. Okay, for a circularly polarized light, which is coming because of the introduction of the quarter wave plate. But I don't know whether it's a right circular or a left circular. To know that, I put another quarter wave plate at a certain angle, 45 degrees to the 45 to the to that of the your previous quarter wave plate, first quarter wave plate. So that essentially becomes as a half wave plate. Now, depending upon what was the initial state, if this half wave plate has a transmission axis parallel to one of the linearly polarized, so it will project as linear or horizontal, linear or vertical. So that is what you essentially are saying that I am going to do an Hadamard operations again. But in the case of an interference experiment, that information is lost. In fact, that forms the basis of what is called as a very nice experiment on quantum correlation. Normally, we say that in a Young's double slit experiment, that once a superposition has happened, okay, so we always do an intensity based measurements. So then the phase information is lost. Hanbury twist experiment was evolved to measure the intensity correlation of two different sources. So you take the intensity, create an interference pattern, and then again allow them to interfere and try to see whether that information is really lost or it is created. So that is given by the Hanbury twist experiment, which later on, if someone is interested, we'll have a discussion on it. Okay, but yeah, but that information is lost as soon as you create on the slit. So now in this experiment, if I have to carry it forward, you have to think how to introduce an additional Hadamard operation so that I can recall back my original state 0 and 1. Okay, in this Young's double slit experiment.
Yes, sir.
So in polarization experiment, it's easy to do. You introduce another quarter wave plate, but in this interference experiment, can I put one more double slit in front of another double slit and try to find out what is the superposition of those two states? Okay, so whether I'll depending upon, so that is an interesting question which one can take it and think that I create two double slits, keep at different distances, and try to study the resultant interference pattern. What is it? Does it lead to a really an interference pattern, or does it leads to the only bright and dark screen? So I leave it as a question, open question, and the implications of this answer to this question are very, very enormous. It's not a very easy. I mean, if you do it properly, you might get a publication out of it. Okay, that's all I will say. Okay. Any other thing? Okay. Yeah. So we move on to the next gate, what is called as swap gate and Fredkin gate. So as the name suggests, swap gate is nothing but it's an gate which will interpose or juxtapose the state wave function. If psi1 and psi2 are two inputs, then the resultant will be at around the same line as will be swapped in between. So psi1 will be taken in place of psi2 and psi2 will be determined by psi1. Okay, so that is the role of the swap gate. So you can construct a logical sequence, so 0, 0, 0. So you, since both the states are in 0, the swapping will also remain as 0, 0. Same thing will happen for 1, 1. But if a 0, 1 will become 1, 0, 1, 0, and 1, 0 will become 0, 1. So that is the logic. So instead of now you can see the difference is from the identity matrix that instead of 1, 0 here, it is 0, 1, and 0, 1 will be replaced by 1, 0. So this 2 by 2 matrix at the center of this matrix denoting the swap gate is going to be interchanged, and that is what it leads to the change of the state. And traditionally it is in terms of quantum circuit state psi1. So you can see psi1 has actually been swapped and it goes to psi1 here. So the way to, so this is a block diagram. So I have something. So psi1, this is a rail. So the rail is from psi1, it goes to psi, it emerges as psi2 because of the operation of this swap gate, and psi2 will be remain as psi1, goes to psi1 because of the operation of this swap gate. So this correspondence is important. It's not that it travels goes below; it just swaps the gate. Okay, because of the action of that. And what is so important about it? So now that you have studied entangled states for a long, so you know that if you take a tensor product, some of them are separable, some of them are non-separable. Non-separable states are called as entangled states. And most of the 2-qubit operations will, when the tensor product, product state operation is done, it leads to an entangled state. But in the case of swap gate, you can see that the states are preserved as it is, only that the position are same. That is to say that in terms of mathematics, it maps an arbitrary product state to a tensor product state. Okay. So in any arbitrary tensor product state, it remains as a tensor product state. So that is the power of this swap gate. Where will it use? It doesn't seem to carry any significance, but we'll show that where it can be used on when we try to create the circuits there. So similarly, like in the previous case, we have to worry about 0, 0. So write down the operations, what is going to perform on each of these gates, and that will help you to construct the operator form for the swap gate. So 0, 0 is the basis on the identity. Same thing 1. Okay, so this is one set. Okay, so yeah, 1, 1 will be negated. So this is one set, and second set will be acted on the I identity into this combination. Okay, so yeah, and now the next challenge is how do we implement this with 3C NOT gate. Now you can see that we are trying to, in the CC NOT gate, we have used a combination of C NOT gate, because as in your digital electronics, we have identified certain gates as universal gates. So that is to say that if those gates are used, then I can construct a combination of those universal gates to mimic the function of the other gates. That is why they are called as universal gates. So NAND gates are one of the universal gates, or in a combination of XOR, or the exclusive OR gate. So similarly, we can see that C0 gate is being repeatedly used and shown that how it can be used for construction of the different gates. Now, if I use a controlled swap gate, then it has a particular function, so which is also called as Fredkin gate. That is, the idea of using the control gate is that I have a complete control. The name itself denotes that depending upon the initial state, only when the system is ready to perform an operation, then only the system is allowed to evolve. Because quantum mechanically, you know that if I keep the state in its any combination, let's say even if it is a ground state, the Hamiltonian operator will act on it and the system can evolve, propagate further. H cap acting on psi will be evolution as e raised to I h t into the given state psi. So with time, it is going to evolve into some different state. Okay, so there is a chance that it may evolve into a different state at all. So that should not allow, that should not be permitted here. So what we do is we require, because in competition we require precise control of the operation so that the results are meaningful. Otherwise, you don't know on which state you have operated, and therefore the results will be hard to interpret, because the results will be based on the what is given as an input to the as an input information or gate on which the operator is acting on it. Okay, it should not be any arbitrary. First of all, yeah. So because quantum mechanics is slightly more sensitive, because the operators for any given physical system are very basic, or are very specific to given choice of basic vector. So like say if I'm doing an intensity based measurement, then I'm only worried about, I mean, in the case of optics, then I'm only worried about the number state, presence or absence of photons. So there the role of polarization vector does not matter. Okay, even if I introduce a polarization vector or polarization optics, it does not play a role. Either the light has to come out or it has to disappear. So same thing. So that is to say that using operator which mimics the function of polarization does not give any credible information if I am just looking at the presence of the intensity based measurement, which is depending on the number state of the photon. That is, presence or absence of photons is what is required. That is only the amplitude information is required. So that means to say that I have made a wrong choice of basis vectors. Therefore, the operator itself is ill-defined. So that is what it means. So to avoid such situation, we require to have a complete control of the any combination. So that is why these control bits are used. And if you require to swap the state from any arbitrary tensor product, then I introduce a control bit gate here, and that is what is called as Fredkin gate. Okay, so only when this is 1, the states are allowed to swap. Okay, so Fredkin gate is defined as identity as 04 and 11 into the U-swap operator. Now comes to the, so that is basically defining the basic, what are the different quantum gates which is known to us. Okay. Just give me 2 minutes. Someone has come. I just want to sign something and I'll come back to you. Sorry for keeping you waiting. Yeah. So now we'll move on to the next big thing which we have all started. Our aim is to create a computer, and we know that the digital computer works on the different gates which are based on the or what is called the logic gates, NAND and XOR, OR and NAND. So all the classical logic circuits are well known and being used extensively in your electronics based computation. So now we have to show that what are the gates which you have created. So what are the quantum mechanical gates? You have NOT gate, which is single qubit, and then all the Pauli matrices, that is X identity operator. Pauli, there are two phase gates are there, Y and Z. And then you have two qubit gate states, which is C0, Hadamard gate, which is an important one. And then a combination of these two, which is called as CC0, which can perform. Then you have a swap gate. So this forms the basic states where you have created superposition of different states and the different action. Now what we have to do, just like in digital electronics or digital computation, we have to find that equivalence of this quantum mechanical gates into the same thing as what is your classical counterparts. Okay, so that is what this aim of this section is. So the action of the NOT gate is to negate it first. So NOT of X acting will be X bar or the negative X. That is to say that it will lead to 0 if X is 1. If the output will be 1 if the initial state is 0. That is what this function of, and this minus X stands for the negation of the gate. So that function is provided by the NOT gate, which is called as an X gate in the Pauli matrix. Okay. So that is one of the Pauli operators, X. It performs the action of the NOT gate, which will take from 0 to 1. Okay. So now if you have to do the measurement, so this is my measurement operator. So as I said that any operator which is going to introduce, this has to span that entire space vector. So that is, I'm choosing M1 and defining this as direct product or the outer product of the state 1 1, such that the the operator M1 has eigenvalues 0 and 1 with eigenvectors 0, ket 0 and ket 1 vectors. When the input is 0 and the output is 1, so that is going to flip the state if I use this kind of a operator there. And the measurement gives a value 1 with the probability 1. If on the other hand, if the input is 1, the output is 0 and the measurement yields 1 with the probability 0. Okay, or in other words, it yields 0 with probability 1. So that is what the basis of defining this M1 vector, which is the measurement vector for this NOT gate. Now the advantage of using this, because quantum state can be in a linear combination of 0 and 1 state, so that I can write this psi as A0 plus B1, where A and B are corresponding probabilities. Now if such a state exists in the classical case, then it's not going to perform any operation or the NOT gate operation. But when I'm applying a quantum mechanical operator, it's going to flip this gate from 0 to 1, because there's no concept. Because digitally, you cannot have a 0 and 5 states simultaneously. Okay, either it can be 0 or it can be 1, but it cannot be in between. That is what the Boolean algebra teaches us. Therefore, any linear combination of any of involving 0 and 1 is non-existent in classical computation. Whereas quantum mechanicity, it is allowed, and that is where you can see the power. That not only it is acting on this kind of a linear gate, one, but it can act on the superposition of this state also. And the action is that it can flip the gate with the flipped probabilities. Okay, so therefore, yes, I have found that my quantum mechanical NOT gate or X gate performs the operation of the NOT gate classically. And for the CC NOT gate, I can write as 1 1. So I have when two control bits are 1, then only the X gate gets flipped, and that is what is written here, which is called as CC NOT gate or set to 1. Then the next we move on to what is called the XOR gate. So XOR gate is now this is one question which we are trying to. This is a classical XOR gate. Okay, so whenever I have, what does that mean? Is if I have a state 0 or 1, addition of them will be either if one of them is 1, then the output is always going to be 1. So I don't know which one of the initial state was 0 and which one was 1. Okay, so that information is not there. So if I have to reverse this operation, that is not possible. So it's not reversible. XOR gate is not reversible. To make it reversible, what we do is we carry forward this X qubit and allow that to be propagated so that I can make it unitary in nature. Okay, so that is what we do when we are defining the XOR gate. So I define the function. I mean, what we have done is we are defining it in the classical sense about the reversibility of this operation. That classically, and that is where the power of this Toffoli gate comes in. That whatever is carried forward that information, which later on we call it an control bit. That because if I take just a simple operation acting on y, then it is going to give me the resultant x plus y, I y, x a small x into XOR operation of y. So that means my initial information is lost. Now with this, if I carry forward and then there is a resultant, I know what are this operation, the initial vectors here as well as the resultant vector. So if I have to go back, I can always take the initial vectors and perform operation. So that gives me the path of reversibility. So classically, this is how we are going to do it, and quantum mechanically, the same function is done by what is called as C naught gate, or where the control bit is always defined as 1 or 0, and then depending upon that, the output of the target bit is flipped. So that operation, which is normally used as a C naught gate in quantum mechanics, is exactly what we define in terms of unitary XOR gate. Okay, now we are not going to talk about the XOR gate classical. Classical XOR gate is non-reversible. Okay, because once this information is lost, XY goes to X plus Y, I mean X XOR Y, then that information of the initial state is lost. So it is irreversible. Whereas quantum mechanically, this unitary XOR is reversible provided we carry forward the initial state X and allow it to propagate along with the resultant operator. Okay, so that only alone will allow it to make it reversible. So this is a test it is possible. So now what we have done, we know the NOT operation, it can be done. XOR operation is nothing but the C naught operation. So two of the classical gates can be done. And also XOR gate can also be done by using CC NOT gate, where allowing both the initial state to be 1. Sorry, the initial gate is fixed to 1, and then this is your sorry, the first qubit of the CC NOT gate is fixed to 1, and then you have another qubit on which it's going to act, and then it leads to XOR gate. So CC NOT gate also can used to control, or sorry, not control, is also used to perform this XOR gate. Okay, so that is what it means here. The next gate is what is called as a AND gate. So the AND gate, you know that when x is equal to y is equal to 1, then only the output is 1. If any one of them is 0, it becomes 0. Okay, so that is a function of the AND gate, which is denoted as by this particular symbol, which is shown here. So this is the symbol for AND gate. So this is again, now you can see that if the initial state is 1, 0, then the output is always going to be 0. If it's 0, 1, output is also going to be 0. If it is 0, 0, again output is 0. But only when it is 1, 1, then you get 1. So for the resultant, if I have to make it reversible, there is no way I can go back and reconstruct my initial states. Okay, so therefore, the AND gate is also irreversible. Okay, so same thing that we did for defining the XOR gate. To make it reversible, we carry forward the initial state xy and then define that, okay, this initial allow the function xy0, it will give me x, y, and x and y. Okay, so if we can carry forward the same prescription using XOR gate, we can reconstruct it and make it this classical gate also reversible. And that is a separate that is a strategy which we are going to use. So what we have to do is that we have to keep both x and y for f to be reversible, such that x is equal to when x and y is 0 implies that both x and y is equal to 0, x is 0 and y is equal to 0. So any combination of it is always going to be 0. So then we can construct based on this argument, use the basis vectors 0, 0, 0, 1, 1, 0, and 1, 1. Construct this as a basis vector which will be multiplied by I, and the last gate is multiplied by the NOT gate. So acting on this particular state, so that will give me what is called as the quantum mechanical AND gate, okay, which is unitary in nature. So you can verify that if it is acting on the state x, y, 0. So this is my operator. Remember, F is a classical operator here, and unitary operators or quantum mechanical operators are acted by this operator U, which is denotes unitary in nature, which is possible only quantum mechanical. And the role is function AND gate. So x, y, 0, that is my initial input to the given state, will result into x, y, x copy, and x and y. Okay. Only when so you can see that 0, 0 will always give 0. If it is 0, 1, then this, so this is like two control qubits. Okay, so only when both of them 1, then this state will flip to the other state. So when x and y is 1, then only 0 will become 1. Okay, otherwise, if any one of these x and y is 0, 0 will remain as it is. So that is what the role of the AND gate is. Okay, so you can carry forward this initial state x, y, 0 and combination. So 0 goes to an AND gate function here. So therefore, I can define and perform this. So this is nothing but we can use the CC NOT gate, but only thing is that in this CC NOT gate, to perform this operation as unitary AND, a quantum mechanical AND operation, the input has to be a zeroth state or the ground state. Okay. Only then I will get this an output, which is called as so this operator denoted here in the figure will perform as an AND gate. So three of the classical gates has been obtained by using this kind of a combination of the function. Now we will move on to the next important thing, because you know that AND and OR gates are used to perform all your operation, multiplication and subtraction and addition. Okay, so that forms the basis of any computation purpose. So OR XY is nothing but the just opposite of the AND gate. So depending on if both the states are any one of the states is 1, then the output is going to be always 1. If Only when both of them are identically 0, then the output will be 0, or else if it is 1 1, it is 1. If it is 0 1, it will be 1. If it is 1 0, that will be also 1. So in all these cases, it will be always 1. For the other cases, it will be 0. So just like the opposite of thing. So immediately it rings in your bell when you are giving us an input and trying to construct it. So what does it mean? That if I have to use this kind of a gate, I have to invert it. So now, is it allowed? Yes, it is allowed based on what is called the De Morgan theorem, which says that the function of OR gate is nothing but using negation of the negative x ANDed with negative y gate. Okay, so basically, so if my input is xi, I have to negate it 3 times, then I can get what is called as the resultant output will be something like what is called as an OR gate. Okay, so that is what is being done here. So xy. So because here also in this case the input information is lost once the operation of OR is performed. So I don't know what is x and y. So therefore this gate is also irreversible. To make it reversible, I carry forward that information x and y in certain form. Okay. So that is what is being done in the case of, so when you're carrying the information, it is basically you use a combination of C naught gate where the or the use what is called a control qubit. But here it is slightly different in the case of x because x has to be negated, y has to be negated, and then you take a AND function of it, which is nothing but a C naught function. So if you take that AND function, then you get what is called an OR. So you are going to again negate that. Okay, so that's the not gate function. Only when these two are not, when these two are negated operators, that will be active, then only the 0 will be give the resultant output as this one. So, so if my x, y, and 0 is the input state, the unitary matrix that represents F, which is representing OR gate, will be represented as. So now you can see the basis vectors have changed. 0 0 1 1 is acted on the negated here. 0 1 1 0 is negative. 1 0 0 1 is negative. And 1 1 0 0 is preserved as it is. Because if it is 1 1 state, the output is 1. 0 0 state, output is 0. Okay. So only in the other case, when any combination exists, that the state is indeterminate. Okay. So So that is what defines the unitary operation of the OR. So basically all the gates which are classically allowed is possible in quantum mechanics also. That is what it's showing. And how do we implement this function? So you have this xy0, so which is resultant is minus s minus x and that. So that is what is being done. So my input is x, it is negated, not gate is used, so I get a minus x here. I get a minus y here, which is because of the negation or not operator x or the x operator acting on the state y here, and then I'm carrying forward. This is my input bit 0. So this is my input to this, and when these two are control qubits are 1, then it performs a NOT gate. Otherwise, it gets carried forward to the other one, and then since it has to perform, so 0 has to be flipped here. Then that is what is going to be has to be negated again, and that's what it leads to one more negation, which will lead to the performing the function of your OR gate. Okay, so uh, please go through over this diagram and once again satisfy yourself that indeed this circuit diagram, this is called a quantum circuit, is actually performing the role of your unitary OR operation. Okay, so as you can see, by negation the first appear in the OR gate, since we have already considered NOT gate and NAND gate. Okay, we are using the fact that okay, NOT gate. So based on this, you can always construct the unitary matrix from this diagram. So writing down what is the, so you know that how to perform a quantum mechanical operation. So you take this identity matrix along with this Pauli X and then act on the given state 0, 0. So this action, the resultant action will result into a unitary matrix which will lead to the function of the OR gate. Okay, so this function will be reduced to this expression here. Now you can write this in terms of, so after rearranging this term, after all this operation, it will be simplified to this function. So this is, you can do as an exercise and satisfy your, that you are going to generate the unitary OR operation. Okay. You know that NAND gate is a universal gate in the digital computation. So same thing, can it be obtained quantum mechanically also? The answer is yes, if I use CC NOT gate. Here NAND is defined as NAND of X or Y is nothing but you have an and negative, so that is what the rule is. So basically I have a C NOT gate, I know that it defines here. So I have to introduce one more NOT gate there, which will be essentially performing the role of the NAND gate. So basically what we have shown that NOT and OR, XOR and NAND gates can be all obtained from the CC NOT gate. So therefore the CC NOT gate becomes a universal operator which can mimic any function of the digital computation or the classical computation or classical. So what it says is that we are ready, if at all, if I'm going to construct a quantum computer, if I am able to identify this gate operation, then I should be able to do perform any kind of computation here. So what is essentially mean that whenever, what questions or what pointers does it lead us to? It leads us to the fact that if I have to identify physical system, first thing is that yes, you require a 2-qubit state. Then I require to perform a computation. So for that, I require it to find out the corresponding operator which will mimic the function of CC NOT gate. Okay, C NOT gate, and if you know the C, if you can control a C NOT gate, then I can always control it, make it as a CC NOT gate. And if I'm able to construct a CC NOT gate, it essentially implies that I'll be able to carry out all my classical computation on this quantum computer. Okay, so that will be the strategy which is going to be used. So with the, and this is the basically CC NOT gate. So you can see only one particular class of gate of quantum mechanics is used to construct all the classical computation. Whereas there are some other operators like a Hadamard gate and swap gate, or what is called as a Fredkin gate or Walsh-Hadamard gate. The only thing now we have to introduce what is called as a phase operators, Y and Z. Okay, which is very essential to introduce, because though in the Hadamard we say that the essential operation is only restricted to e raised to I pi, then that is introducing a phase difference of only specific amount. But you know, this quantum mechanical wave functions are continuous, so therefore I require to introduce a continuously varying phase, and that phase operation also requires to be defined. So if I'm able to identify all this, so my criteria for looking at what is called as exploiting the power of quantum computation is that I want to, because the whole paradigm which we started with was I can express the parallelism, what is called as the massive computation power it derives this comes from the parallelism of the circuit which the quantum mechanics allows you to do. What does that mean is if I have to do a perform an operation in classical computation over n number of operations, I have to do it sequentially. But in quantum mechanically, since from a 2-qubit state, I have the option that it can be in any of the 0 and 1 state and or a linear superposition of that, where alpha 0 plus beta 1, that is 0 and 1 are my excited and ground state. So it can be any kind of a superposition state or a linear combination of these two states where it can be continuously varying. So what does it mean is that there are infinite possible ways in which these two systems, these two states can combine. Okay, if that is so, then I can perform the operation on any number of operations simultaneously on these two states to yield an operation. So that is where this derives. I can do parallel computing. That means I can act on the states simultaneously. Okay, so that is where the power of quantum computation derives. But then to derive that kind of a power, I require to create a superposition of states, which is done by the Hadamard operation. So this is completely classic quantum mechanical in nature. It is not. It doesn't have any classical counterpart. Okay, so Hadamard operation is one of the very important operation which helps you to, along with some additional phase operator, it will help you to derive the maximum benefit or whatever is the quantum computation power. Okay. So before we move on to that, so there is one theorem, what is called as no cloning theorem. So we know that what is a no cloning? Clone means an identical representation of the original. That is what is called as cloning. Another way we say that we copy the data and create a same copy, identical copy of the original state. Okay, so classically, yes, we do it. We are very good in this. We take anything and we can reproduce the classical data. The question is whether quantum mechanics allows it or not. It just turns out there is one theorem that which says, given by Wouters and Zurek and Dix, that unknown quantum system cannot be cloned by unitary transformation. So far, we have used only unitary transformation or the unitary operator as the choice of operator to perform any computation here. Okay, so that is the forms the basis for us. Now, what does it say that if I have an unknown system of which the initial states are not known, then I cannot clone it by using any set of unitary transformations. That's what it says. The proof goes as follows. Let's assume, so it's a negative proof, what is called as. We assume unitary that there exists a unitary transformation U that makes a clone of the given system. What does that mean is, I take a, suppose, let's say operator U or the unitary transformation U acts on any given state psi or whatever this phi you can call it, phi, such that phi acting on U, unitary acting on phi 0 will take it to, so basically 0 is an empty state. Okay, here the 0 is an empty state, the initial state is phi. So the action of this unitary operator is that I create a identical copy of this phi and make it here. So that is what. So not only the initial state is preserved, but the output state also is the same as that of the initial state. So that is the action of this unitary operator or the, let's say, cloning operator U. It creates an identical copy. Okay, so that is what it shows here. Now whether it is possible or not, let's see. Okay, so let's, these two phi and this particular state are the two states which are linearly independent. Then we should have acting. So these are two linearly independent vectors from the same basis state, and let this unitary operator U, which is called a cloning operator, act on this. So phi 0 will act on this, will create phi phi, and same thing is over here by definition. Okay, so that is the action of the cloning operator. Now let's take a superposition of this such that the psi is described as a linear combination of these two initial states, phi and psi, yields. The action of this cloning operator on this is I take this as a composite state. So this is called as a composite state. This linear combination of these two states is a composite state psi. So I require when this is acting on this, so I require to create another psi here. So that is what is being done. So I act now, since these are linearly independent vectors, this composite is nothing but comprises of these two linear independent. So this one I can act on individually of the basis vectors. So the unit operator acts on the basis vectors, which creates this composite state. So phi 0 and phi 0. So it will lead to this particular state. Right? So this is one way how the system is going to evolve or assume to be evolved. So now, but this is a composite state psi. So I will create a so identically, ideally, U should be a cloning transformation. We will take from psi to psi. So if that is so, and then I rewrite in terms of its linear combination of these two basis vectors, I create the state which is half phi phi plus phi psi and this one. So I create four different elements here. Whereas if I look at the action of this acting on this composite state psi 0, it gives me phi phi plus phi phi. So definitely this composite state, the resultant composite state by the action of this cloning operator seems to be different in the way we are performing this operation. And in reality, we know that unitary operator has to give us something which is unique value, which cannot give some contradictory results. So what does it mean is our assumption that you can actually clone the initial state for any arbitrary system is incorrect. So therefore, this shows that there does not exist a unitary cloning transformation, and hence there is no way to clone a system by measurements. A measurement is probabilistic and non-unitary, and gets into the component of the space which is in the orthogonal state of the observed subspaces. So, so you can see now with the question which was posed earlier in the interference experiment is that if you are doing, so if I am projecting the interference pattern on the screen or measure it using a photodiode, then there is no way I can know in which state it was 0, 0. Because it has collapsed into one of its combination states. As long as if we don't allow it to collapse into one of its basis vectors or in its eigenstate, then you can keep on performing unitary operation. Because what happens is then you have, since you have collapsed into one of the states, all that particular resultant information is lost, which is infinite in nature. Okay, so therefore you cannot get back the original results as such. So for to perform the operation and to get back the original one, you require to not to collapse the state and then still act the particular operation, unitary operation to reproduce the original state. Okay, so therefore the action is there is no way to clone a state by a measurement. The measurement is probabilistic and non-unitary in nature, and it gets rid of the component of the state, which is orthogonal complement of the observed space. Okay, so this is a small exercise based on this discussion, and you can write down this as an outer product and show that the result of one is such that U does not exist. That is, the two, this cloning transformation, the transformation is not possible, even this kind of a combination. So that's what it is. Shown for any arbitrary phi and psi. Okay. Okay. So does anyone has any questions on this? Okay.
Hello, sir.
Yeah, please.
So, are there any new ways or research going on so that we can clone a quantum state other than using this unitary transformation?
Quantum mechanics restricts you the choice of the kind of operators you can use, right? There are
Yes.
something called as non-demolition measurements, mhm, called as Q and D, which apparently you say that you don't collapse the state into its any of the eigenstate, you preserve as it is, and still you are able to get away with the value which you can obtain. Okay, so that is one class of research which is going on, which is saying that it can be not done. I mean, it can be done preserving the without the loss of information or without the sacrificing that the massive parallel computing power which the quantum mechanics derives from having superposition of different states. Okay, so there, but when you are trying to do this quantum computation operation, you like the results to be deterministic, right? You want some numbers to work on whether the event is happening. It may be probabilistic in nature, but the numbers have to be real. So
Yes.
under that condition, the unity transformation will restrict some class of operator, and there is no way you can do that. Okay, so that is the outcome of this discussion. So whether there are those Q and D measurements performs a different class of operations there. So maybe I'll touch upon that the topic briefly in the next class. Okay, which will deal with this measurement.
Sir, is this type of measurement similar to weak measurement? Like we are not they have both the same idea. Uh,
Yeah, yeah.
in
Weak
order to,
measurement is based on some kind of a Q and D measurement. Yes.
oh,
That
okay.
you do such an operator so that it does not disturb the initial state too much, so that the original state is preserved as such. Yeah.
Okay, sir.
It is based on that kind of a concept. Yeah.
Thank you, sir.
Any other question which you can have, or now you can think about the corollary there. Just one second. Yeah, yeah, please. Yeah, so I was just saying, if anyone doesn't have question, I'll just make this remark which is stated here. So how do we store the data? Okay, data is nothing but an exact copy of the some state, and the states are having the information there. Okay, so what is it allowed is in quantum mechanics is that you cannot clone an arbitrary state. Okay, so an arbitrary state which is given psi in some combination of psi a0 plus b1, which is unknown factor, that cannot be cloned. But if I know what is the number's expected value, what is a value, then that is forms a particular state, and so that state I can make multiple copies. That is where I mean, surprised that no one asked me that question. When we are trying to make the system reversible, what are we doing in the XOR gate? We are carrying forward that control bit, right? The control bit operation is that you carry forward this information so that the system becomes reversible. In the OR gate or in the NAND gate, wherever, AND gate, to make the system reversible, I am going to carry it forward. So that forms the role of this control bit. Okay. So that means a particular combination of this gate is allowed. So that means I am preserving the data here. So I know the initial states, I carry forward without destroying it. The operation is acting on this particular combination, but the data, since this carried forward, is available to me. So in a way, I'm trying to clone this kind of a system which is being used here. Okay. So the no-call theorem in principle says that we cannot act on the any arbitrary state. But if I know what is a formulation, then yes, I can store that information. I'm just trying to say the move very hard. Good. So that is what. So the loophole is that the theorem does not apply if the states of control are limited to 0 and 1. So 0 can go as 0 can act on this. So we can choose any unitary operator whose action is predetermined. Then we can have this set and make a copy of that data set. So that is where there is a option as to proceed with this quantum computation here. Okay. Because many a times you will be misguided by the fact that the no cloning theorem will say, now it is something like this. In postulates, we take an arbitrary operator A, which is a non-eigen operator, acts on a given state psi. So what is the output? A cap, which is a non-eigen A operator, acting on the given state psi. What will the resultant output? It will emerge into a different state, let's say psi prime, right? Because since it's a non-eigenvalue equation, it's a non-eigen operator, so it's not going to deal into any of the superposed states. It's not going to collapse the system into any one of its eigenvalue or any of the eigenstate. It will just transform itself into a new operator. So that forms the basis that, okay, that forms the basis for choice, making a choice of a different set of operators which will act on a given state so that their actions are predetermined toward different values with certain probabilities. Okay, so that is as to say that if I choose wrong choice of an operator, then it is going to disturb the state from its initial state psi to a new set of states called as psi prime. Okay, so that is what the quantum mechanical postulates are based on. So here, if I make here it is slightly different in the sense that I don't have a, if the knowledge of the state is not there, then I cannot choose because operator has to be predetermined from what is the given eigenstate of the given system. So I have to find out what is the state, how it is defined, what are the basis vectors, and based on that basis vectors only and only alone we can identify what are those unitary transformations which can be allowed. And even among that given state, if I'm not able to prepare the state properly, okay, that is very, very important when we come to the deviation criteria, that you have to create what is called fiducial states, initial fiducial states. That means the initial states has to be unambiguously determined. You should precisely know. Only then you can know the action, because you can predict the action of an operator on those states such that it evolve into something else. Okay, and then you measure, you to know the outcome, you perform a measurement. So it's so as to say that unitary operator cannot act on any arbitrary state to clone that state. That's what. So with that note, I will just stop here, and then in the next class, I will discuss about the deviation criteria and take up a couple of physical realization systems, whatever I can do, 2 or 3. Okay. So if you have any questions, you can. So can I stop the presentation? If you have any questions on the slides, I'll keep it on. If not, I will switch off, stop the presentation, so that we can discuss anything, whatever you want to. Anyway, okay, so I'll stop the presentation. So still anyone has any question? So please feel free. Any comment?